Okay, so we're going to look at Lisp, and I've already given you a tour of Lisp, and you've started on your implementation, so you understand Lisp to some degree there. And if we were to just look at programming in Lisp, that introduction I gave was probably enough for you to go to the Common Lisp manual and go and understand how Lisp works. Okay. So what's going to be different in what I'm going to talk about is that I'm going to actually talk about implementation. Okay, so we did a few concepts last time. One for your part assignment to part one, you need to write recursive Lisp functions. So you've done recursion in Java, so you can think recursively, and you have to basically translate that into Lisp. And to give you practice with that, I gave you a simple function, simple by Lisp standards at least. And we saw through this function also the general syntax of a function. So this function, I've actually expanded on that syntax in this example. So I did run the, just as Nathan's coming in, I did try out the load example that Alec had put on the web, and it does work. So I wrote this function in a file, and I then loaded the file, and I said, while you're loading each particular line, please go and print out the result of each line. Okay, and it did print out as advertised. And why did I? And so I'm printing out the result of each step, each expression interpreted by Lisp. And one of these expressions is the definition of the function f. And we see here that the function f this is a slight modification of what I gave last time to make debugging easier for you. So if you're writing a recursive function in Java, you just step through the debugger, you go and see the values of variables, and you can fix your problems, hack your way through it if you need to. Lisp, there probably are debugging environments, but I don't know of them. So we can resort to, as many of you do, using print statements. Okay. Well, in Lisp, everything is an expression, not a statement. What we think of as statement will have to return some value to, and a printing of something will print out the value on the console and return that value as a result of the expression. Okay. So what's kind of unintuitive, it was to me when I saw it first, having learned Lisp many years ago, was the fact that you have a function name, you have a parameter list, and usually in Lisp, after the parameter list, you have one result expression that you evaluate, and that is the result you return back. And here Lisp is becoming more like Java, like conventional language, and it says, oh, in a function you can have multiple things after the parameter, and we call them statements in regular languages. But since these are not statements, they're expressions, we call them expressions here, and you can evaluate many expressions. Okay, so you're evaluating many expressions, which is the result you're going to return. But the last expression you evaluate will be the result. Okay, so the syntax, this general structure, you can say, is that you have to have a returned expression. But before you return the expression, you can evaluate many other optional expressions. Okay, so they can be 1 to n. So in my example above, I have one optional expression, which is printl. And I'm doing that so that I can print out the argument I'm getting. Okay, so if I'm debugging and I'm getting a Stack Overflow problem, I probably want to go and print out what am I getting each time. Okay, so in any recursive function, you have some base cases, and you have one or more recursive cases. In this example, we have two base cases, starting with EQ, and then we have one recursive state. And the recursive step basically calls the same function again, and the recursive step should be a reduction of the original step. So the way we are reducing it is that we are taking the list we got, as long as it has um, um, as long as it has a cutter, a tail, okay, we go in, maybe I should have checked for atom too. No, because when I do carl, I'm going to take care of the one element case, okay? And so we know that there's more than, there's one or more element, there's one or more elements. So what we will do is we will go and recurse on the tail of the list we got and see and check if that meets the criteria we're looking for. Okay, so each time I'm going to actually go and print out the argument I get in the recursive function. So when we go in, I have two expressions in this file that I loaded. One is applying the function to list 1, 2, 3, 4, 5 with the argument 2, with the member 2, and second time with 6. Okay, and 6 is not found and 2 is found. 2 happens to be the second element. So when we evaluate it, I go and first evaluate. First, my list is 1, 2, 3, 4, 5. The first element is not equal to 2, so I recurse. And then when it comes 2, 3, 4, 5, the first element is 2, so I stop the recursion. Okay. And the second time, I keep recursing till I get to the nil list, and then I say no. Okay. So this is basically 101 level of recursion, really, if you do recursion in 101. Okay, but it's, when I presented this example to you, there were some blank stares. So since it's an unfamiliar language, so just to make this more clear, I've got the tracing. Okay, questions? Okay, so that was one thing we saw that was new, and then we saw a whole lot of evals. Okay. And one source of confusion based on what I've seen from office hours and Piazza is how to decompose one of these function applications. Okay, so each function application happens to be a list, and we gave a general structure of the list earlier. And notice that the elements of the lists are always heads of something. The elements are never tails. Tails are the next pointer. So I saw some example on Piazza where somebody was saying, hey, I evaluated on the tail and here's the issue I got. So you really shouldn't be accessing tails. Okay? So even if there's only one element, one argument to the function, that argument, or even if it's a list, that will be an element that is inside the outer list. Okay, and so you saw that in the plus evaluator, that when we got the E1 and E2 out of this application of function to two arguments, both E1 and E2 were heads of something. Okay, and so that's an important point, because even in the string as list, some of you were having trouble with printing that out, and one of the Piazza comments I saw said that, hey, you should be looking at the heads and not the tails. Okay, so this is something that you have to be careful. You might not, your tests might have passed for adequacy, but they may not pass for correctness if you're messing up somewhere here. And this is visualized again here, that this expression was adding up 4 and 5. Was doing two additions, and you can see that all the elements, the plus, the first plus, the second plus, the head, the 4, the 5, and the 2 are all heads of something. Okay, so this is something to be in mind. And what I saw on Piazza was somebody saying that, look, I took something's tail and I eval on that, and that's not what you do. Okay, so the quote example. Now, in this quote, what we do is we pass to quote an argument that happens to be a list. Okay, so that's why you may think, hey, I've got to take the tail. But that happens to be a list embedded in the bigger list, which is a function application. So even though E will this expression E here in our example is plus 1, 2. A list containing 4 and plus 1, 2, and 5. It is the head of something. Okay, and again we see that here, that in the result of expression, the result of quote happens to be the head of something else. in something in the input expression. Okay, this is something we saw. Code just returns this argument and takes out the code and returns the value. Okay, this is where we stopped last time. And we said that and the nice thing about code was you give it a list of elements. You just type in the elements with the list, and it gives you another list with the arguments unevaluated. So what if you wanted the arguments evaluated? We saw there was a list function. So list takes E1, E2 to En as arguments, and it returns back a list containing those elements. And those elements are now evaluated. Okay, so we go and we have to compose together the eval of all the elements that were passed to list. Okay, so this is where we were last time. So I've got some blank statements. We know that we have to evaluate E1, E2 to En. There's no doubt about that. How do we compose them together? How do we compose them into a list? Good. So you have to call a factory to create the object, okay? And we have to do this recursively because we have, you can do it iteratively too, but recursively is good because you're going to be programming in lists. You might as well get practice with recursion, okay? So I'm not going to show you whether it's iteratively or recursively. I just got this ... So at the very top thing, I'll have to have a new instance, right? And that will take as an argument the very first argument, the first head E1, and then the second argument is where the recursion will happen. So I'll go and do another new instance and pass to it E2, and the last one will be the one before En, right? And new instance takes two arguments. So we know that En.eval will be the first argument, and what will be the second argument of the last new instance? Null. So if you pass null, Java will not complain because null is an S expression. But this was a confusion that a lot of you guys had. So it's not null, but the nil atom. Okay. So we really want to pass the nil atom, and that's because that's how lists are composed. Okay, so this was probably one of the more difficult evals you had to do in your assignment. The other ones were simpler because you don't have to do this recursion. So questions on this? So here's a question now. It's an efficiency one. Should I be, in general, when I create atoms, I use a factory to create atoms. There is a I use a class and I do a new on a class to create an atom. Okay, so I want to create a string atom. I go and do a new string atom, pass it the string. I want to create a new number 5 atom. I do a new int with the thing. So and nil again has an argument with the string nil. So should I be doing calling the factory to create? Should I be doing creating a new object here when I create a nil atom? Should a new object be created at this point? So because Andrew's code doesn't have a nil atom factory, we would create a new object, right? But could we? So that's what Andrew did. Could we avoid?
I think in my code, but it is like if it ended with the nil atom, I just use that one instead of making a new one.
So you said I have this nil atom around, so why not use that, right? And Andrew probably did something very similar because I didn't see the new instance being created. And you did that because it doesn't matter whether you reuse a previous nil atom or you use a newly constructed nil atom, right? You could use the previously nil atom because of the property. What property? Again, just to... They're all S expressions, but I think, yeah. All nil atoms are the same because They are nil, right? So could I play this trick with something else? Supposing I had to compose, forget this example. Supposing I had to create an atom with the value 10. Could I play a similar trick and not construct a new atom, new integer atom? If I had somewhere a 10 atom for 10 around, I could play the same trick, right? Because all atoms are immutable. In fact, all expressions are S expressions are immutable. Okay? So I could generalize this idea. And those of you who've done compilers, have you seen this concept somewhere of saving a step by reusing something especially for literals, reusing something you've done for a previously computed literal when you have to deal with a new literal again? I don't know whether you guys do this in your compiler class or not. So if I was to assign to A the number 10, okay, first, you guys know more about the modern machine architectures than I do, but let's go and figure out. When I assign to A the value 0, let's say I know the address of A. I need to assign I need to store at the address of A the value 0. How do I get hold of the value 0 in machine code?
Isn't there just one section? I think it's like position 0, like $0. That's just a 0.
So is there a location in memory that just has 0? So, these locations don't appear by magic. We have to, in the compiler, generate code to go and store things in locations. But that would be a good idea. You have?
I think there's a register that just contains the value 0 in a lot of processors.
So you're saying maybe it's not a memory location, maybe it's a register. Somebody want to go even further? I'm sure these machine instructions exist today. I think they existed in my time too. But there are instructions that say for 0 and 1, because 0 and 1 appear so often, that add, load 0, load 1, so that you don't have to worry about storing it in memory and so forth. But let's go to Andrew's point of having a memory location for 0. So what would the compiler do? The compiler would say, look, 0 is used a lot, so let's go and put a location in memory for 0. And maybe that 0 is always loaded in register. Okay? And maybe 1 also is a very popular one. What if I go and use the number 1789? How do you load 1789 into memory location? Your statement says A equals 1789. We know the address of A. Yeah. Sorry, yeah. Sorry? Yeah, so address of A you've got. How do you get 1789?
You said the bits of that location could correspond to that number.
So you have to find another location in memory and go and store in that 1789. Right? You set the bits. And then you have to go and load the value 1789. Right? So you set the bits. Now what if I use 1789 again? Because I'm a bad programmer, I don't use named constants. Okay, so I use the magic number 1789. 1789 is actually that's the independence here. American independence 1789, or is that French? Okay, I just picked that date from trying to remember my history. Okay, anyway, so supposing I go and use 1789 multiple times, never explain them. So I use it a second time. How to do the same thing, or can I do something smarter?
You can just go back to the bottom where you stored it.
So you can go back to the previous memory. For that, you'll have to have in the compiler a literal pool table. Do you guys study that in compilers? Literal pool table? Literal table? No? So you just keep the literal table of maybe a fixed length, because you don't want the literal table to get very long, and you say if I've seen this number before, allocate the address so and so for it, so I'll reuse that address. I could do the same thing here. Every time I construct an atom, and I asked Andrew to do it actually, and he said, no, that's too much work, I won't do it. I've got too many things to do right now. So you could keep for each, for each string that you create an atom for each number you create an atom for, a table that says, given this number or string, here's the atom. And if I see it again, I'll go and, if somebody says construct an atom for 1789, I'll say, well, I've already constructed an atom 1789. If I have, I'll just return back that atom. Okay? So duplicate atoms. So create a new nil atom. Atom factories can return. If we had atom factories, as sort of Nathan suggested, we could return previous atom that's equal to the one you want, and these are all immutable. And there's compiler might create a single address for all reference to literals, such as 10, a literal table. And current Lisp skeleton does not have atom factory, so duplicate atoms created. And with an interpreter, I can see going Andrew's way, because with the compiler, we don't mind how much time we spend on the compile time, because we care about runtime. The interpretation is happening at runtime. So looking up the table may be more costly than just doing a new. Okay, so there's a trade-off. So I'm not saying that this is always the perfect thing to do, but I do want to sort of point out that there are things like literal tables and in compiled languages, and the analogous thing here would be to create an atom table of some kind. Okay? You could create, in fact, since everything is immutable, you could even say that whenever I'm asked to const 10 and 20, and that happens a lot, return back the previous structure I created. Okay, you can even do that. Okay, and that's kind of what happens with strings in Java. If you go and say hello world 5 times, it's not going to go and create 5 different string objects. It's going to try this out. Go and say A equals hello world, and then say B equals hello world, and check if A is equal to B or not. And you'll probably find that A is equal to B. Okay. However, if you say A is equal to new hello world, string hello world, then it says, oh, you really want a new object? It'll give you if you want. Yeah, Andrew.
I was just going to ask if you can do that.
Yeah, you can do new, and I don't know why it gives you a new object. Say you're being foolish, I'll give you back the old object. But maybe you just want to try it out. Okay. So now let's look at car. Okay, and this is going to be a little tricky. At least I'm going to confuse you enough to make it tricky. And I've confused you in the very top thing by having an extra parenthesis, which I didn't want. So that's a typo. So we get E. Okay. So we know that this is a function that takes one argument, not like, this is like quote, which takes one argument. It's not like plus or cons. Okay. So we get this E, and it's got okay. So I think there's a typo there too. Yeah, sorry. So it's got one argument, and we can go and just go and assume that E happens to be something with a head and a tail. Okay, and return the head. Okay, so we're supposed to do a cons. We're supposed to do a car. Car should be done on composite structures. Okay, so we can assume that E is a composite structure with a head and a tail, and we just return the head. And if it's an atom, things will break, but who cares? We don't expect any mistakes. Okay, so my label E is wrong. It should be at the head. The head should be E rather than the whole structure. So will this work? Let's go and see. Or should we do? And here's a choice we have. Should we go in after doing the head? Should we do an eval or not? So there's always a question to eval or not. So I got the head. Should I go and do an eval after that? Okay. So there are many questions here. Should I just go and get the head first, and when I get the head, try to do an eval? So let's go and just take some examples. And so that's what I would return in this case. So if I have car of cons 1, 2, with this algorithm, what will I return? So with car of cons 1, 2, I should return 1. Right? So I didn't quite say what should I return. Sorry? So it'll return, so one answer is that the answer is 1 because that's what the answer should be. The other one is that the answer is 1, 2. Because the structure really is car. So remember that we have a list. This is very confusing here again, always. The list is pointing to, so the tail, the E happens to be this structure here. This is the E. This is where the E is labeled wrong. E is really this. Whenever you're decomposing a list, they're always heads. This is a point I want to make again and again. Okay? So this is my E. So what will this head be? So it will be cons. Right? And then the tail will point to another structure whose head will be 1 and 2. So what will I return here? Anybody, somebody other than Nathan? What are we going to return here? We're going to return cons. Okay, so what's the mistake here? Nathan's kind of got the answer already, but anybody? Yeah, Andrew?
So you're good, from E, you're going to the head, and the head's the cons, and so you're just talking about on the cons, but it's not taking into account the tail.
So you should do a eval on the
Head of E.
on E, right? So that's what we need to do. Okay, so this is wrong. This was wrong here. E dot get head was wrong. So now we are going to do a take 2 and do a E dot eval. So we're going to do an E dot eval and go and get another structure, and this one now has, we're going to look at that structure and we're going to find its head and tail, right? And we're going to go and do the head of that, compute the head of that. Okay, so now cons 1, 2 will evaluate to a structure. Cons 1, 2 will be called. It'll return back an object with a head and a tail. The head will be 1, the tail will be 2. So we're going to go and return 1 as we really wanted to do in the first place. Okay. So again, the key here is that evaluated operations are not stored, and we need to go and first get rid of the operations in all the sub-expressions before we go and operate on them. Okay? So to confuse you a little bit more, okay, so let's go and see what happens here now. Will this work? So the cons will go in, I mean, or do I need to go in? So you're saying it recursively will evaluate? So the cons, when we go and call eval on cons, cons is going to go and say evaluate my arguments, and we are going to get 3 as we want. Okay, so what if I go and do a eval on the head? I mean, is that something we should be doing? You know, it seems that the more evals we do on the argument, the things, the better it is. So what if I go and put a little extra eval here? Will it hurt? Is it needed? Will it hurt? Is it a no-op? Or is it something we should really do? Good, good, good. Okay. So as Nathan pointed out, and as we pointed out, our original eval was recursive. It went and evaluated everything. So we don't seem to need to go and evaluate. And not only that, we might run into trouble. And if we do that on the first case, we'll evaluate one again. Evaluating one again will always give you one, so no problem. But if we go and do this, so even in the second example, the result is 3. We evaluate 3 again, no problem. Problems arise here. Okay? Because here we've got plus 1, we've got a quote there, and the quote is going to return plus 1, 2. And what we'll end up getting is 3, because we did an extra eval and we evaluated plus 1, 2 to 3. Okay? So we have to be careful that we evaluate before and then we just get the head, we don't go and evaluate it again. If that happens to be an atom, no harm done, we just did an extra step. But if that happens to be a function application, then, or if it happens to be a list with 1, 2, 3 in it, like you were saying, then we'll try to evaluate the one and say, hey, where's, you're not a function name, so that'll be a problem. Okay? So this is not what we want. So this is not what we want. Okay? The extra eval is not what we want. So we don't want h.eval. Okay? And we can see, we can trace a car eval. We see that we first create, a lambda calling expression with 3, 4. Okay, there's an eval call before that. And then we go and do a car on that structure and get back 3 in this example. Okay. And with the quote, we again see that we get plus 1, 2 because we did the we got the car and we didn't do an extra evaluation on the plus 1, 2. So this is just showing you the trace to show that it's consistent with what I talked about. And Qadr is going to be just very similar. Rather than doing a get head, we'll do a get tail. Okay. So that's your Qadr. Okay, and we can convince ourselves that. Okay. Now we come to the easy ones. Atom evaluator. Okay, so again we are S is equal to F E. E we know is the head of head object. And we can just go and do an is-atom. And should we do a eval of E before we check is-atom, or can we just do E dot is-atom? So if we did this, we said atom 5, that would work, right? The E is 5. When we check 5 is atom or not, it'll return 5. So can we imagine a situation where we really should do an eval of E before we check whether it's an atom or not? So I just took my E, simple thing, I just said is atom, and it works in this example. And the question is, should I do an E dot eval before doing the is atom? So what should this answer be? It should be false. What is plus 2, 3? Should be true. Gets confusing, right? So this will give nil in our current answer. It should really be true. So we should really be doing E dot eval, which is kind of what you were saying. You were saying this, we should do it, and then you came up with it. Then you got confused.
So you want is atom to keep going down?
Eval will go down. It depends. If there's a quote somewhere there, it
Yeah,
won't.
I know that. I'm just saying, why is it the fact plus? It's like if you did quote plus 2, 3.
Then it will be false.
False.
which is what we want. Or, yeah, or list 1, 2, 3. It'll be false. Okay?
I mean, isn't that kind of like a design choice? Like, couldn't you do it the other way? Like, why do you need it to be evaluated? Yeah.
So you're saying atom could be defined differently?
Yeah, sure. And like, I'm just wondering if there would be any downsides to having atom plus 2, 3 return nil.
I mean, atom semantics become different, right?
Yeah.
So in general, you're saying is something that I compute, is something, if you're going to say is 5 an atom, you already know that is an atom, right? Atom becomes much more interesting when you go and compute some value and you don't know whether it's atom or not. And if you don't do eval, you don't compute, so what use is that atom? Think about it that way. Right? So you went to a list you don't know anything about, and you went and wanted to know whether the 7th member is an atom or not. For that, you'll have to go and evaluate, and you get back some value, and you say, is the evaluated value, you don't care so much about what somebody input. You want to know the S expression that you got from the input expression. So the semantics are that is my argument an atom or not? Not as you typed it, but as evaluated. I can indeed define an atom that says, is my argument, don't evaluate the argument, okay, and tell me whether that's an atom or not. Okay, and if I really want that, I quote that. And then I can figure out then I will get back the unevaluated atom. Okay, so it's code 5, it will return 5. I can check whether that is an atom or not. Okay. So it's the same principle you could have said in other cases, right? When I do a car of something, is what I have there something that's directly a structure or something that computed to be a structure? And as it turns out, for these composite S expressions, you have to compute them to create them. You can't type them in. So why not? It's more uniform to say that we're going to evaluate the expression. Okay, but indeed, I can define. We're language designers. We can do anything we want to. But in this, yeah.
So I may have missed it in there. What is the exact reason that we need to repeat that versus function?
What's the exact reason? Happens to be programmability. Okay. What do you want? And I try to argue that if I just said, did you literally type is the literal atom there, unevaluated atom there? That's not a very interesting atom, because you probably know it's an atom or not. There's some mystery when some mysterious function computed it and returned the result back, and you want to know whether I got an atom or did I get a sublist. You're traversing through the list. You want to know whether some element of that list happens to be an atom or a list itself, or some composite structure, some tuple. So you should evaluate to figure out, to find that element. So that's the reason. Okay. And think about it. This is a general thing. Lisp is kind of funny because some things are not evaluated. But whenever you call a procedure, and you think of atom as a procedure, the arguments to a procedure are in general expressions. They are not lists and they are not variable names. So if I go and pass to an atom Java function 5 plus 7, wouldn't Java go and compute 5 plus 7 before sending it to the atom function? It's not going to go and send you plus 5, 7 because, well, we don't expect that in Java. Java doesn't have these function applications. So this is far more consistent with what you guys know. And it's very interesting that now you're so Lispish in your mindset that you even think, hey, why not just go and pass the whole structure plus 5 through, because you can. So you're thinking of alternatives that you wouldn't have thought had you just worked with Java and not worked with Lisp. Because whenever you call a function in Java or other languages, you're passing expressions without an L value. L value is something, is an address. What you pass to a function may not have an L value. It may have only R values, which are expressions. And those expressions always get evaluated before the function is called. And not evaluating it is inconsistent with what you know already in other languages. Okay, so Lisp, like I said, is kind of in between. It does some things that are different and some things that are similar, and that's why there's a cause for confusion here. Okay? Questions? And what will the answer here be? What are we going to do when we do atom car? We're going to call car, and the car is going to call cons, and cons is going to return 2, 3, and we're going to do a car of that, so that will also be true. Right? Even though what we are passing is a similar situation to the previous one. Okay? Okay, now we come to the easiest one. Okay, or maybe it's not. Maybe quote is the easiest. Or maybe, okay. So, I'm sorry. This is EQ and not eval. No, this actually, I'm not even sure what the right answer should be here. And nobody's ever sure, right? I mean, in Java, what is equals? What is equals? It's so confusing, isn't it? So what do we really mean when we say E1 equals E2? Are E1 and E2 equals? So let's take some examples. EQ22, you expect true, right? Whether we create a new atom or not, they're equal, right? If we don't create a new atom, so I shouldn't have had the right column showing up there, but what, here, EQ const 2, 3, const 2, 3. Are you happy with nil? Are you unhappy, really unhappy with nil? So you can see why it did that, right? It doesn't want to recursively go and do equals on the structure by default. So Lisp actually, common Lisp leaves this ambiguous. You can return nil or you can return true, and as it turns out, return nil. Okay? I wish I'd got the animations here. Okay, now supposing I do set q L to const 2, 3. Okay? And I set q L2 to L. And set q is something we haven't implemented. But when we studied Lisp in the beginning, we saw that set q is really an assignment. Okay? And so this comes down to all this shallow copy, deep copy thing we talked about earlier. So if I now do EQ L to L, what do you expect? True? Because we know these are immutable structures. We store pointers. Surely Lisp can compare two pointers. That's no work. Yeah, it doesn't want to go recursively and check things. Yeah, that's work, and but here it can just check the pointers, as in Java. Okay, so this is like equals equals, or this is like the default implementation of equals. Okay, so you'll get T. Okay, so now we know that we've got Java underneath us, and we have to go and process this EQ, and we can just go and do what Java typically does. Okay, so we should evaluate E1 and E2. Okay. Yeah.
Wait, so EQ const 2, 3, const 2, 3 is rejecting nil because we're saying they don't reference the same instance?
Yeah, they don't reference the same instance. In this implementation,
Right.
which happens to be C Lisp, not Andrew's implementation. Okay? So even in Andrew's implementation, I'm saying Andrew is one TA, working only a finite number of hours, so he could have been lazy. We could, in principle, have taken some popular consts that people have done and create a table, saying if the head is 2 and if the tail is 3, let me go and pick up a table, let me go to a table and see whether I've already created a composite structure associated with 2, 3 and return that back rather than doing a new. I could do that. Okay? They aren't doing that. Just as I said, for strings, people do it in Java string. It happens with strings. Okay, so I could do that. So EQ const 2, 3, EQ const 2, 3 is ambiguous in Lisp. Okay, just as equals in Java is ambiguous. Whatever the class does. Okay, by default, what it'll do is, for primitive values, it'll go and check if the primitive values happen to be, you know, it'll do a primitive value comparison. And for user-defined objects, by default, it just checks the addresses. Okay, that's what happens in Java, and that's kind of what you expect here. So when you're doing EQ, if the arguments are not atoms, don't expect any guarantees. Okay, so do EQ only on atoms, or at least one argument should be an atom. Okay, two questions.
I'm sort of confused on the ill-defined part, because in Java, you may not want that behavior, but that behavior is very well defined. I mean, I know that's going to happen. So in this, I mean, in the spec, is it just simply not defined?
So in Java, when you call equals, the spec says whatever the class does.
Right. But that's well defined.
So, you know, this is not the most practical of languages. You can always try it out, right? And, you know, if I was optimizing, so you know what they say about optimizers. You know, if your code doesn't run, turn off the optimizer, right? So whenever you do optimizations, especially with the halting problem, you're just playing dice. And you're hoping things will work as you expect. Not always, but at least sometimes. So I could have optimized it away and created one structure so that because these are immutable, I could have created a table just to do with strings. You know, in Java, if I say A equals hello world and I say A equals hello world again, B equals hello world, does Java guarantee that A is equal to B? A is equal to B? I don't think so. I don't think it will guarantee that.
For strings, you need to use the dot equals.
Sorry?
For strings, you would need to use the dot equals.
But for literals, that equity defined, but like pre-compilation, but it should put it in the, I don't know.
If it's a primitive data type, you can use equals.
Right. If it's primitive, it's equals. And as you're saying, for strings, you normally say equals. But we are going one level beyond. We are saying we're going to optimize. We're going to cheat. We're going to play dice. Okay? And that is that when I go and see hello world first time, I go and create a string. When I see hello world the second time, I don't create a new memory location. I just go and return the same memory location again because it's immutable. So, and then when I say A equals B, I will return true. Even though in general in strings to be safe, you have to call equals. But that's an optimization step. Okay, if the user goes and enters through 2 million strings, okay, they've got a lot of time to type things in. Okay, Java will probably give up and say, hey, I'm not going to allocate this much. So I don't know what Java does. You know, I'm just saying as the compiler implemented, just think. And I suspect that Java says, hey, you know, at your own risk, assume these two things are equal. But in general, just don't do equals on strings, call equals. Similarly, in general, don't do equals on non-atoms. Okay, but if you know better, you know, it's like working with C also. You know, yeah, play around with the addresses if you really dare. And when you get something wrong, you deserve what you got, right? So that's kind of the, you know, and that's fine. If you're an operating system guy, you should, you know, you should really be careful. But Nathan?
I have two examples, and I know that they're sort of specific, but I still want to ask them. So if you have equals L and cons 2, 3, they're not the same instance, so that would be false.
That can return false.
That can be false. But if you have equals set Q L cons 2, 3, L, then would it be pointing to the address that it returns 2.3 from and then gets that address of the L that you just defined right before it, so that's all true? So like equals set Q L to cons 2, 3, L.
Yeah, so that means that L, when you did the first set Q, that cons 2, 3 got stored in L, and then you compared L with L again. So that's guaranteed to be true. Okay? So we will go and do the evaluation. Okay? And we can, if E1 eval equals E2 eval, we always return true. Okay? Now we want to consider the atom cases. In the atom cases, we may not return the same atom. So we can go and say, if they are both atoms, then I just call the get values and see whether they're the same. yeah, because the get values could be strings. So I'm doing equals rather than equals equals. Okay. And Andrew wants me to put, and he has put this extra check in. Sorry, this should have been E1 eval get class equals equals E2 eval get class. This is just playing it a little safer and checking whether the two atoms classes are the same also. Okay. And that's what his code does. And actually, that's something he just recently added. And I'm not sure you ever really need this because his argument is an identifier atom, it's got get value as a string, and a string atom, its get value is a string. You don't want to return an identifier atoms. You don't want to say an identifier atom is equal to a string atom. Okay? You think that's okay?
Well, I mean, even if the strings were the same, like when you created that atom, if its string were an operator, it would be an operator atom and not a string atom. So do you even need that?
So my feeling is that if it's an identifier atom, we never go and return the identifier atom. We always go and return its value, look in a table.
Right.
So I'm saying we never do the comparison.
Yeah.
So I sent him an email yesterday saying, no, I don't see the situation. I haven't got a response back. So maybe he's, anybody who implements, I respect them more than somebody who, like me, just talks about implementations. So he might have some subtle case that I haven't thought about, but I feel that this is not necessary. But it doesn't harm to check the two classes are same. Okay, so there's a typo here with the atom thing that it should be E1 eval and E2 eval for the get class thing. Okay, and I try to fix these problems later. I think I've got good memory, but I'm going to be at some point creating videos from all of this stuff before your midterms, and I might forget at that point. But just remember there's a typo. Okay, if you ever listen to my recording, it'll say that. Okay, let's look at cond now. So, I gave you one definition of cond, and then Andrew gave you all the ways in which you can deviate from this and still return a right value. And I didn't even know these existed. I don't want to know about those cases personally. Okay, I want to expect that you've got a pair of values that C1 to Cn are the first elements of these pairs, and I want to expect them to be all Booleans, expressions, not arithmetic, and I want an accompanying return expression. That's how I learned Lisp, and that's how I used Lisp. But for convenience sake, Lisp has done lots of things differently. So I'm not going to consider all those cases here, where you might have a pair. You might not have pairs, but you might have only one value in the pair. Andrew pointed these cases out, and if you've handled them, you get extra credit. You get lots of extra credit, in fact, because it's such tedious stuff. And so, I shouldn't say tedious, that's a judgment. It's programming intensive step, okay? So let's just go and look at this normal case where you are, do I have an extra pair of extra parentheses here? I suspect I do. I don't think I need, I forget now. So do all the pairs have to have an extra parentheses around them in Lisp?
Yeah.
You do? You do. Okay, so it's a list of things you get. Okay, yeah. So, so here's my definition. Okay, we evaluate C1 to Cn. Okay, we do all the evaluations, and then we find the first element in that list that returns true, and we find the corresponding E in that. So if Ci happens to be the first element in this eval list, then we go and return Ei. We evaluate Ei. So you guys have now got into the evaluation business, so we should do the evaluation also. Okay, so this is my second try. And I'm going to argue this is not quite right. So let's go and see with some examples. No, I don't need that extra parentheses, do I? Lisp is confusing. No, no, I don't. Do I need this one? I don't need this particular parenthesis. So this was my mistake. Okay. So yeah. Okay. So I mean, it's just instinctive to go and expect the function name and then the arguments to be within parentheses. In fact, McCarthy, who invented Lisp, his initial syntax was not plus 1, 2, but plus with 1, 2 coming afterwards in the parentheses. So it is kind of confusing, and I got confused there, I guess. So anyway, so what should this value be? So I'm going to argue that this is not correct. Again, I'm being very careful. I'm saying, let us, when we are given this cont expression, let's go from E1 to En, evaluate all of them, and then pick up the first one that evaluated to true, and then find the corresponding element in the other case and evaluate it. Yeah.
Yeah, I don't think you want to evaluate all.
You don't want to evaluate all of them. You want to do lazy evaluation, right? You want to evaluate only those expressions that matter.
Yeah, because you wouldn't want to set QA nil here, right?
Yes. So the question is, if I evaluated everything, did I just do some extra work, or did I harm the result in some way? So is it an efficiency thing or is it a correctness thing? And as you're pointing out from this example, that it's a correctness thing. Because at the end of this, we want to return, the value that cont will return is, of course, 1, right? But the question then becomes, if I type A at this point, what should the value of A be? In this case, it will be, given this algorithm, it will be, but you don't want that to be nil, right? So that's important. Yeah.
We just have a break when it comes across the first base.
You have to break when you catch the first one, okay? And that is, when we talked about lazy evaluation, that is lazy evaluation. You evaluate only. So, this thing I said, in normal languages, you evaluate all the arguments beforehand, right? So if you think of this cont, these being arguments to cont, you have to evaluate all of them. That's what normal languages give you. But you see, but in Lisp you cheat. For quote, you don't do it, okay? And for con, you do kind of do it, right? So this is wrong. Only C1 to Ci evaluated in C1 to Cn. And this is also important. We don't just go and evaluate all E1 to En either. Okay, that's kind of obvious. This is important though, that we evaluate only EI. We don't evaluate the other ones. So if there's some set Q in the instead of 1, if I'd said set Q beat 1, only that gets evaluated and not that gets evaluated, but the second one's set Q will not. The second set Q. Okay, so we will do it. I'm not giving you an algorithm or a loop, but we were basically saying that let's go and figure out first C1 to Cn, and then let I be the first member of C that evaluates to T, okay? Which means formally that, Ci.eval is true and C1 to Ci are all false, okay? And then we'll get the result back, okay? So it's important that you don't evaluate all of these. Okay? Questions? Okay, and you see here that I've got EQ50, EQ00, EQ55, and you see that EQ50 has been evaluated, EQ00 has been evaluated, but EQ55 has not been evaluated in this trace. Okay, so this trace is consistent with what I just talked about. Okay. Okay, now I come to the easiest one. Okay, and yet we'll spend some time talking about it. So you're given a function with one argument, and that function happens to be eval, and eval just returns e.eval. Okay, so it's just giving the user a way of calling eval that exists inside your interpreter anyway. Okay, so if I did eval of plus 1, 2, the result is 3. No?
By definition, let's eval does it one more time. Just one more time once.
So you're saying you eval a second time?
Yeah.
Okay, let's go and see. Is that, and the definition you got from where?
From I looked at the formal definition of eval Lisp, and it's on some weird HTTP site from this, so I don't know. That's from Lisp.
Yeah, I think you actually have to do that.
Really?
Yeah,
So,
You can go to Y because of quote. You can go to Y because of quote, but the definition of eval is in 20.
let's go and see. I've got some Recursive results right here, I believe. Or maybe I didn't check Recursive because I was so confident. Surely I'm not wrong there. Okay. Plus 1, 2. What will that give you, by the way? So eval of plus 1, 2, even if you go and do eval twice, the result is 3, right? We agree on the result? Who knows what's going on inside? The result is 3? Nobody doubts that? If I type plus 1, 2, the result should be? So we have all this discussion, eval once, eval twice, eval n times. Why do we have an eval? I mean, why do we have an eval function? I mean, why make the user type an extra eval?
So that you can eval twice. Because if I just typed in 3 into the terminal, it still evals that to 3. So by calling like eval 3, it's going to eval it again after you've already done it the first time. This is by definition. So if you were to do eval quote plus 1, 2, it evals quote as plus 1, 2.
Okay, hang on. You're going too fast for me. Okay? I'm calling eval on 3. Eval on 3 is going to say 3 eval yourself. Eval was called only once, as far as I'm concerned. The internal eval was called only once. Let's make it very clear. There's an external eval, there's an internal eval. The internal eval, the S expression eval method is called only once in that case. Okay? And so that is my question. I could have, as a user, just typed plus 1, 2 and got 3. Or I could have typed eval plus 1, 2, and that eval function, that's your evaluator, is going to take its expression and do an eval on it. Okay? And that'll return 3. So why have this confusing, I didn't know it was so confusing. Why have this apparently confusing eval function given to the user when the system automatically evaluates it when you type an expression? Plus will do the evaluation, so why do we have to go and do it recursively at one more level?
Because it's useful for other operations, and not necessarily that useful for plus, but like when you did quote, like it was actually like.
Okay, it's because we have quote. That is the key. Because we leave things unevaluated, we have to go and evaluate them later. Okay? So why explicit eval? This has to do with the fact that in Lisp, code is the data structure. That means you can go and store code as a data structure and later evaluate it. And we saw how to go and do that. So code can be stored in variables and executed on it. So I can go and say setql quote plus 1, 2. Okay? So I get now plus 1, 2 stored. I've stored plus 1, 2. It's an application. At some point, I hope, I should be able to use it. So I go and eval L, and I get back 3. Okay? And again, there are 2 evals here. There are, in fact, 3 evals in your world. There's the eval the user types. There's the eval on the S expression. And there's the eval on the evaluators that you register. They're all tied to each other. Okay, but we're overloading the term eval. And as far as I'm concerned here, I have done eval only once on an S expression, on the plus 1, 2 and S expression. There also happens to be another S expression that is eval, that is eval as the first element. I did an eval on it, which went and did an eval on its EE there. Okay? So, what's the harm? Let's do another eval. Let's try to be, I have done only one S expression eval in my implementation. Nathan and you guys all want multiple evals. So I just go and do the eval here and make my behavior work like yours. So if I do eval on eval plus 1, 2, what happens? What's the result? The first eval will return, the innermost eval will return what? And eval of 3 is? Okay, so no harm done, I just wasted some work. Can you imagine 2 evals causing problems? Chris, I'm going to look at you. Yes, okay. Eval, list 1, 2. What will the inner eval return? A list with 1 and 2. What will the outer eval try to do then? And expect the first element of that list to be? Operator. Is 1 an operator? You can type it in your C Lisp. Okay? And this is the result you'll get.
That's why you don't do that.
Sorry?
By definition, that's why you don't do that.
Yes. So if I had gone and done 2 evals there, if I did e.eval again, I would get the same result. So this is why I'm saying,
Is that not the expected output?
yes, 1 is not a function, it's the expected output.
Then you want to put e.eval, not eval. You want to put 2 evals, because it inherits the expected output. And e.eval environment, .eval environment gives you the expected output. Eval list gives you an error. That's the expected.
I don't know what you're saying. Okay. Put it there, and it should, unless you're doing something funny, because my eval is equal to your, my 2 evals is equal to your implementation with 1 eval. Okay, that is, we'll turn off. So I better go and make sure that there are test cases that catch you if you're doing that. Okay. And because you can't go in, why would you do eval twice? Eval, and this is what I want to make. Cascaded evals. And maybe you're talking of 2 different evals, which is a different issue. So eval A equals, eval A is equal, yeah.
I think some confusion is in the sheet. There's an example of a eval that's like eval and then quote should like quote 1, 2 plus 1, 2 returns 3. Even though if you have it with just 1 eval, it should just return plus 1, 2, right?
Is this something that Andrew put in? I mean,
In the sheet, it says that eval of quote plus 1, 2 should give you 3. Therefore, you have to do it twice. It would evaluate quote plus 1, 2 to equal plus 1, 2, and then evaluates plus 1, 2 to equal 3. And that's how eval quote plus 1, 2 equals 3. You have to eval twice. You can't not.
yeah, because you're calling 2 functions. You're calling first a quote.
You don't call eval quote plus 1, 2. You call eval quote plus 1, 2. And in the operations, eval is how you make that happen. It evaluates quote and then evaluates that in the 3. Unless you wrote the documentation wrong and we all did it wrong because he wrote it wrong.
That was Andrew's quote. That was Andrew's stuff there. Quote 1, 2, when you evaluate the quote, it'll return back an expression. There'll be an evaluate that quote does, which is return just 1 plus 1, 2. And then when you're given eval with an argument, that plus 1, 2 is evaluated, and evaluate will call evaluate only once.
You only evaluate it once. You only evaluate the head of quote, which means it evaluates to. So
So is there any, are you saying that my definitions here will not give you a result here, the definition of quote and eval? Is anybody saying that?
But I think, I mean, it's just like in the sheet he was given, like.
No, forget sheets. I didn't write that stuff. I didn't even read that stuff. Okay? That was Andrew's stuff. Tell me whether my definition is going to give you a wrong result.
It will not give you 3. It will not.
I don't want to go back to my slide because I'll lose the recording. So, I forget, in fact, what example you were talking about with the plus one too. But
Quotes, yeah, it's eval, parentheses, quote, parentheses, plus 1, 2.
okay, so my
I mean, it's got, I think it's just got like confusion, like there's been like,
so you're saying
yes, the example, that was like an example we were given with the result being 3. And then you're just kind of saying that it should be, plus 1, 2. And so I think there's just a divide on like,
so maybe because I didn't implement, I haven't considered that case carefully. So you'll call eval on the top level. It'll call eval on the quote,
Yes. Yes.
which will return plus 1, 2.
Then you dot eval it again twice.
Oh, the result has to be evaluated.
Yes.
Yeah, it's the
You
result.
don't-
It's the result that's
Yeah.
valued.
You don't eval parentheses eval. Just with one eval, it should.
Okay, I get it.
Yeah. Okay. You get it.
And what if you didn't have a quote? What if you had a list?
Then it, as expected, would break. Just like if you said in C-list, it flows an error, right?
But if we only have one,
If you only have one eval, by the method of evaling twice within that function, it should go an error. You eval list 1, 2 the first time, which gets 1.
No, what you'll have to do is check if it's a quote. And then, so that's kind of funny here. Because if there's a list 1, 2, you're going to evaluate that list 1, 2 a second time.
Don't do that. That's why you don't do eval list 1, 2, or you put that in documentation that should eval to. Yeah. It breaks.
Does it break?
Yeah.
I can't run my stuff, but I did the test it, so it probably does.
I think with that,
Sorry, say it again?
It's not in the list of things like you tested with plus and you tested with everything else. It didn't say that you expected an output for a list.
I mean, I should have thought of that.
Go by documentation.
So if it's got quote, 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 you evaluate one quote, you're saying, and you leave it at that. So you're saying in Lisp eval of something that returns a list is going to be just erroneous. Yeah.
I think maybe some of the confusion is that whenever you pass like a compound expression or something that can be evaluated to a function, when you read in that argument, the argument to the function, you evaluate the argument. So what's being said here is that when you call eval and then an eval on a quote, when you're passing the quote in as the argument, you evaluate that argument, which evaluates down to the function, and then the eval function evaluates that argument.
Right, but what if the return value is a list?
Then it fails.
Then it fails, as the C list would.
No, it doesn't.
C list doesn't.
No, it doesn't. Yeah, that's the problem.
So either way, either both my solution and your solution are
I
wrong.
think both. Yeah, I think that's.
I was considering the list case and you were considering the quote case,
Yeah.
and I just handmade those in one case.
I thought eval list. I thought eval existed because of quote.
So unless you go look at the result back and go and say, so I would rather be, I would prefer the answer to be quote 1, 2. I would prefer the answer not to be 3 now.
Doesn't Sealess does 3 though? Yeah.
So what does C-list do?
Yeah, it gives 3.
Put it up and try it.
But no, what's its algorithm?
I have no idea, obviously.
Okay, so we'll have to go, this is a good point to break, so yeah, go ahead. Sorry?
It breaks. Eval list 1, 2, right?
It breaks? Yeah, I don't like those semantics, but okay, that makes sense. So just to quickly review some of the more subtle things we talked about last time. One issue was we were looking at the list function, and the list function had to go and create a nil atom at the end. And the issue was, do we create a new nil atom? Do we create a new atom whenever we need it, or should we reuse atoms? Okay, values we've done before. We've created before. And right now we create a new atom whenever we need it. That's what Andrew has. But we could choose the alternative strategy of reusing atoms, and that concept exists in compiled languages also. I mentioned that. And let's just look at that a little bit more in depth, because it's an important concept and we had a lot of discussion on it. So let's first talk about reusing atoms. Okay, so let's talk about just focus on integer atoms for now. So if I go and say plus 12, 5, I need an atom 12. I need the atom 5. So when I need 12, I can allocate 12. I can store a table. I can keep a table where the value 12 is the index, and the atom that encapsulates it is the value, is the object that I'm storing in the table. So I've got 12 that I've referenced. I go and say, okay, if I need 12 again, I've got this atom here that I can look up. 5, similar thing we can do. Okay, that's going to compute 17. So I can go and put that in the table also. Okay. So far we haven't really gained much. We've had to go and access tables, which is slow, depending on how big the table is and how good your hashing is. But we are assuming that we might reuse these values. So this is where we reuse them. So I go and say minus 10, 5. We haven't seen 10 before, so we go and allocate 10 also. So our table's growing. Okay. And we are looking up each time. And then we need 5, and now we are paying dividends. We looked up, we're reusing 5, but we had to pay the cost of looking up. Okay, so there's a trade-off here. And the result of minus 10, 5 is 5 again. So we again don't allocate, and we just go and give a reference to what we already have. Okay. So this is the basic idea of having a table. Because data structures are these values are immutable, we can afford to just go and pass a reference. We don't have to send a copy. Okay. Similar concept exists in regular languages, and this happens at compile time. That you go and say, you declare some named constant and say it's equal to 12 plus 5. Okay. So it needs the value 12 somewhere, and so it'll allocate an address for it. And push the number 12 there. It needs the value 5, so it'll allocate an address for it and push the value 5. Put 12 first and then 5. And it'll store this in a table. Okay. So far we haven't gained anything, but this is all compile time. Who cares if the compilation is slow? We mainly care about runtime. And 17, we can even store that if you want. Okay. And again, now if there's another named constant and we say 10 minus 5, we allocate for 10 an address, but for the 5 that it is in the expression and for the 5 that's stored, we can just do the same thing again. Okay. So pros and cons. Allocating addresses is slower at compile time. Okay. But at runtime, we have less memory being used. Okay, so that's good. But for ints, maybe the storage is not such a big issue. Things get more interesting when we look at strings and say strings in Java, which are immutable. So now we go and say some named constant A is assigned hello. Hello is a string, it's a bunch of characters, so we're not just talking about one address, we're talking of a whole object. So we can allocate an object for the string hello. And then when we go and say hello again, because we haven't declared a named constant, we go and say b equals hello rather than, well, I guess we did declare that a might have been a named constant or a variable. So let's assume that a is a variable here. So we didn't declare a named constant. A might have changed value, so we don't say b is assigned a, we say b is assigned hello again, because we didn't do a named constant. So this kind of tells you why you should do named constants. And we can reuse the value. Okay? We can. We are not guaranteed to. So this is very important. When we go and talk of languages, languages don't provide you with the full specification typically. There's always something called implementation defined. And the whole idea there is that the language designer said, you know what, my head is aching at this point. I'm not going to make any more decisions of this kind, so I'll just leave it to the implementer to do this. And this happens in almost every language I know, except perhaps Ada, which was meant for the military. And you didn't want any guesses as to what was happening there. But often languages just say, it's up to the implementation. Okay? So whether you allocate, you're not guaranteed that B and A will share addresses, but they may. Okay. So if they do, then you're always told for strings do A equals B rather than A equals B. If B happens to be a named constant, you can always go and do equals named constant and to compare with that string. So that's another reason for using named constants. You can just use equals, which is faster. But in this case, it'll return true. Okay. And even the equals in string is going to first check whether it's an equals, and then go and do a string comparison. So even your equals will become faster if they happen to share the same address. Okay? So this is why a table like this is useful. And if you say C equals new string hello, you're going through all this effort of saying new string, so you must want a separate location. You must want to somehow make A and C not be the same when it comes to equals. So at this point, we'll allocate a new object in memory. And so if you really want to see whether, so A equals C will be false, but A equals C will be true. Okay? So that's this table that we were talking about. And I'll try to fit this into your assignment somehow, because I think it's an important concept. Okay? So we are not just talking Lisp, we are talking languages, so this will be a good language concept. Any questions on this? Yeah.
When we invoke C equals new string hello, the entry is added in the runtime or compile time.
So this is being done. So typically this happens at compile time. Okay, so they'll go and write the code to allocate the object, and they'll say, okay, this, they'll go and say A and B happen to will share the same addresses. So we'll go and write the code to. I mean, the memory will be allocated at runtime, obviously. Okay, but the fact that this table is kind of confusing that way. But the fact that this will be allocated from the heap, okay. But you can take a note there that we've allocated something for hello, and the next time somebody goes and refers to the same hello, we are going to refer to the A's allocation and not allocate a new thing. Okay, so we have to do some bookkeeping there, but the actual address will be created at runtime because it's allocated from the heap. But we've just noted down that we've got A already allocated here. So whenever somebody else, whenever B needs an object, we will go and just take the object. So we'll kind of need two tables. We'll need the table at compile time because I think strings generated at runtime, people don't tend to go and see whether they already exist or not. So if you go and say H plus E twice, try this out, by the way. I haven't tried it out. But go and say A equals H plus E and then say A equals H plus E again. I suspect A and E will be not equals. Okay? If they are equals, then we can do this whole thing at runtime. We don't have to have compile time part at all. Okay? But if we are going to say that no, only the things appear at compile time that somebody typed in, those are the ones we will go and make equivalent. Then you would need to sort of have something at compile time and runtime. Compile time to say that, look, these two things are in the same equivalence class, and runtime to actually have the addresses. Okay, but if I get a chance, I'll do it, but if you guys get a chance, just try to see what happens with computed values. Okay, and again, it depends on the compiler. The compiler might just do nothing. Okay? But what will happen at compile time is that they'll generate the code to make sure that when we go and do the new, we load the address of an existing object rather than of a new object. Okay. Questions? More questions? So comparisons are faster at runtime, and this is more space efficient at runtime. And if you're doing duplicate items, then I guess the compile time is not really that much faster. It's actually you might generate less code, so maybe this little faster. I'm not 100% sure of that, but certainly more space efficient at runtime. Okay, if you're only doing this for duplicate items. Okay, for non-duplicate items, you become slow. You go look up the table. Questions? Okay, then we looked at car and Cutter, and we saw that we basically have to take the car of some expression. So that expression better be have a car and Cutter part, not the expression itself, but the evaluation of the expression. Okay, so you will go and do the eval of the expression, and then get either the head or the tail. Okay, and in the case we've got Cutter, which is we're getting the tail. Okay, so this is important that you evaluate the expression, then figure out whether it's a composite or not. Okay, and we looked at atom then, and atom caused some confusion because of semantics. So we agree that atom of 5 should be true. There was some confusion about atom of plus 2, 3 being true or not, because the immediate argument of atom is not an atom, it is really an expression. So then I showed you atom of car const 2, 3, which is that you've got a S expression with 2 and 3, and you're taking a car of that, and should that be atom or not? Okay, so as it turns out, so the answer is that we have to first evaluate the atom's argument and then look at whether the argument is an atom or not. Okay, so atom of 5, either way, with the evaluate or not, will return true. But atom of plus 2, 3, if we evaluate it, it's true. If we don't evaluate it, it's not true. Okay, so this shows you that we have to evaluate it. And this was somewhat unintuitive to some of you, but if you've done the first part of your assignment too, you must have realized that you need atom to evaluate its argument. Okay, you're going through a list, you're concatenating the string representations of all the atoms in the list essentially. So when you encounter an atom, then you can use a concat operation. So you have to know whether you're an atom or not an atom. If you're not an atom, you go recurse in. So atom, almost a lot of Lisp functions rely on the evaluated thing being an atom. Okay? And your string expression, toString in A2 is going to rely on that. Okay, so questions on this one? Okay. Then we got to EQ, and I said, I'm not 100% sure of something because I didn't really implement this stuff. Andrew did, and I finally talked to Andrew yesterday. So EQ is always confusing. It's confusing in Java. It's confusing in Lisp. And again, as I mentioned last time, Lisp leaves certain things undefined. So EQ of const 2.3 and const 2.3 is nil in Common Lisp, but it could be true also. Another implementation could do that. But if the two objects have the same address, are guaranteed the same address, so they've been stored in a variable and they retreat from the variable, then EQ should return true. And if the two objects are atoms, then if their get values are the same and they're the same class, then they should return true. Okay, that is guaranteed. So the implementation we had first went and evaluated both the arguments, okay, and then went and checked if they are equals to each other in Java. So if they're the same atoms, if they're the same S expressions, we do say they're equal. And if they're not, we go and check if they're atoms. And then if they're both atoms, we can just check the get value, or we can even check the get class to be sure. And I said, you know what, I can't really see ever the get values being the same but not the get classes, and Andrew had put this in. Maybe there's some case I haven't thought of, and Andrew did agree with me, and he said that, look, so right now your A1 doesn't have, we don't even look at identifiers. Basically, those are not even allowed in your language. But when we allow those identifiers a little later today, we'll be comparing the values stored in the identifiers, not the identifiers themselves. And if we were not looking at the values stored in the identifiers, we're looking at the identifiers themselves, then they have a string representation, so does the string atom, so maybe there could be a problem. Okay? But as it turns out, this is just an extra step we don't really have to do. Okay? And I'm going to argue that if we have a literal pool table, then EQ is faster. Why is that? Can be faster, not always. So let's say I'm doing EQ22. If I do EQ22, what path am I taking in this in my algorithm on top? I'm going to evaluate 2. Okay, get back the same atom back. And what I'm going to do next? Sorry? Yeah, evaluate both of them. And what's the next step after that? Before the same class, what am I doing? I'm just checking if they're the same atom. If they're the same atom, I don't bother to go below. That's exactly how your equals works, your object equals works, the string equals work, or should work at least. Just check if they're the same strings. If not, then go into a character by character comparison. Okay, so if there are 2 strings that I'm comparing here, and if they're the same string atom, I'm going to just do an equals and pass. Otherwise, I have to go and do a string comparison. Okay, so it's more efficient if we have a literal pool table. Okay, though the literal pool table, to go and access it is, takes time. It takes space. Okay, then we got to eval. Okay, that's where things got confusing. Okay, and here are the examples I had. And the examples I had, I said, look, we're just going to do the eval once. Okay, and this is the results of, these are the results of the expressions. Actually, I had typed these things into Common Lisp, and these are the results, exactly the results I've got. So we try to justify the results based on the algorithm I had. Okay, and I've put the setQ in red here because we haven't really seen setQ. So that's where some hand waving occurred, and the right result was explained using the wrong reasoning. So we'll go and disregard that and look at all the other examples and verify that given the algorithm I have, you would get the results that I have, even though the algorithm we know is wrong from what Nathan said. Okay, so if I just do the eval once, okay, then eval plus 1, 2 will return 3, right? No dispute. Yeah, forget the set Q here. Eval plus 1, 2, would that return still 3 using, so eval plus 1, 2 will return 3 according to me, and then evaling it again will return 3, so that's also consistent. Okay, and then I also showed you eval list 1, 2, and it says, and I get the message 1 is not a function. So would I still get this using my algorithm on top? The innermost eval will go and evaluate list 1, 2, create a list of 1 and 2, and the outermost eval will go and say, hey, 1 is not a function. Okay, so if you're just looking at quote unquote what Ben said, the scientific approach, just going through some examples, and as long as you don't have any experimental errors there, you have enough samples, my algorithm is consistent with the examples, modulo this set Q thing, which we don't really understand at this point. Okay, so things get problematic using the example I didn't use last time. Okay, that's the one that Nathan came up, which is, and I didn't use this example because it's kind of, why would you go and do a quote and do an eval? Okay, it's kind of uninteresting. It's only interesting if you stored something in a variable and you're evaluating later, because you're storing some program. But so I didn't consider this simple case. And in fact, when I was doing eval, I traced every function, and I showed you the tracing except for eval. I said, eval, we've been doing eval so often. Eval is just the most trivial function, and it wasn't as trivial as I thought. Okay, so if we do this, then quote will return to you the list. So eval will go and evaluate the quote. Quote will return plus 1, 2, and eval will just return that value back because it's just doing one eval. Okay, so you would get plus 1, 2, which is the case we didn't consider, which is not what we want. Okay, so this is not what we want. So what we want is another evaluation. So we'll just hack it and go and put another eval here, and we'll get the right result. Okay, and now with this extra eval, all the other results can be explained. They'll still work because plus 1, 2 will return 3. You evaluate 3 again and return 3. Okay, and we don't know what setQ does. And again, plus 1, 2 will return 3, and so you can do eval n times and it'll still come 3. Okay, and eval of list 1, 2. Last time it was the outer eval that complained with my current algorithm. Now the inner eval will complain, and that's why I couldn't distinguish between these two things. So indeed you would get the message one is not a function, but you would get it because of the inner eval and not the outer eval. Okay. So you all agree that to make this last example work, we have to have two evals, whether we like it or not. Okay, and we've got to figure out now whether we like it or not. Okay, so this is let's go and call this scientific approach. Okay, eval list 1, 2, this is where we got confused. So eval list 1, 2 was not an example that we had last time, but I said, hey, what do you think would happen here? And everybody said, I don't know. And then somebody typed it in and said, well, that is illegal. Okay, so that may or may not be intuitive, and we'll talk about whether it's intuitive or not, whether it should be correct or not. Correct meaning this is how languages should be designed. But so this is consistent with these two evals being there. Okay. So this is, and the reason for the confusion partly is that eval A is equal to A is equal to eval A if A is an atom, but not so if A is not an atom. If you're doing a function application, it's not the case. Function application removes the function name from it. So that's part of the reason why we got, or at least I got confused. Okay. And had I gone and actually traced Andrew's code, I would have seen that the algorithm is as I described earlier. So we have to do an eval of plus 1, 2, and you see a line that says eval of plus 1, 2 is 3, and then eval of plus 1, 2 is 3, and then you evaluate 3 again. You're seeing that you're doing eval twice, eval plus 1, 2, and then eval 3, and these two evals are done up as part of the eval of eval. Okay, so this is consistent with that. So that's the implementation approach. And I want to, and with quote, you're seeing that again, that we go and evaluate plus 1, 2 to 3, and before that we evaluate quote plus 1, 2 to plus 1, 2. Okay, so we first evaluate quote plus 1, 2 to plus 1, 2, and then we evaluate plus 1, 2 to 3, and then that gives us the eval of the whole expression. Okay, so let's go and try to figure out from first principles. I mean, we can't just know all these details. Memorizing a manual is not the way to understand a language. So there should be some first principles from which we could have derived the behavior, and either Common Lisp or Lisp did it right, or what I had it was right, and let's try to decide whether from first principles we can do this. Okay, and what are first principles? First principles means that one first principle is consistency. Okay, good languages, you have to learn a very few things, and then everything is orthogonal. You just compose the ideas together, and there you get the answer. Okay. Bad languages is you've got to remember every case. Okay. And some people think that's a sign of intelligence. I know in London the cab drivers had to take an exam, and they had to know how to get from every place to every other place. Which is basically memorization, but that's, they were probably very good at doing that. And now with GPS, I guess, I don't know how important that exam is. So we'd rather do it more abstractly. So let's go and see something analogous that you might have used, at least I have used, in Bash. Okay? So in Bash, if I do ls, and we saw in Bash we can call an eval. Okay? So let's go and see how eval works in Bash, because that might inform our intuition about Lisp. Okay? And Bash came after Lisp, so maybe they did things right there. So I can do eval of any string in Bash. ls gives me the list there. So if I do eval of ls, what should I get? You get the listing. The same thing as the above. If you're a Lisp programmer, would you expect that? Because the Lisp programmer will say eval twice, right? So I indeed get the same result as ls. So if you do +1 2 or you do eval +1 2, in the Bash philosophy they're the same. Okay, in Bash the basic principle is you can invoke a command interactively or from a program. You often just say system execute this command, is the same thing. Okay, so you're not actually evaluating twice, you're evaluating just once the string. Okay, if I say eval of echo ls, if we were taking the Lisp approach, we'd evaluate twice and get the listing, but we just get ls. Okay, so from that point of view things are confusing. Either Bash didn't do things right or Lisp didn't do things right, but there's certainly not uniformity among these two languages. By that? Sorry?
I don't know what my directory is when I'm doing ls, but I know exactly what I'm making my list when I said list 1 2. So if I already knew my list is list 1 2, why did I call it out in the first place?
Or in Bash you can have variables too.
I'm just saying in this context, I feel it's different meaning.
Because I could have read a string in, when I say eval echo ls, I could have read a string from somewhere that I want to execute. The same philosophy, and so I might want that evaluated. Yeah.
Is this really a comparable situation? Like, when we're talking about a valid list, we're saying, like, we're giving it an actual argument that, like, it can always be run in itself. Where in this case, couldn't you say, like, it is evaluating twice in this case, it's saying that the argument you provided is the name of a function as a string. It's evaluating that string, which would be an atom, it just comes out as the same string, and then it finds that function and evaluates it again.
So Shell has got the same principle as Lisp, that you can go and actually execute commands through eval, and you can compose these commands at runtime. Okay, here you're saying that why did I use ls? Like, why didn't I could have just typed ls, but I could have gone and had an argument to the script, and that argument is a command, and it will go and evaluate that one thing or the other depending on what the argument is. Or I could have read from the user there. So it is meant to do the same kind of stuff. Okay, and in Lisp you can do eval twice, and you would get this effect that I'm talking about. I didn't try doing it, but I believe if I just did eval of echo ls, eval of echo ls, I would get the ls. I believe I would. I'm a little wary of, unless this has got something, unless the shell is disallowing that, it should work, just based on principle. So I should be able to execute commands there, but then I will have to say eval twice. Okay. So one of them is, assuming that's the case, okay, comparing with Bash is not fair, because maybe Bash is wrong. Okay, so we should go and maybe compare with other languages too, and compare with other things Lisp does. It's got to be internally consistent, and it's got to be consistent with other languages. Maybe it's not consistent with Bash, but maybe it's internally consistent, and maybe it's consistent with non-Bash languages. Okay, non-Bash languages, we don't know of eval function anywhere else, so let's just go and look at internal consistency. And now I'm going to argue that Lisp is very is indeed internally consistent. So let's go and argue for the double eval. Let's forget that Bash does it maybe the wrong way. Maybe Bash did it the wrong way. And maybe I'm too much of a systems hacker and I'm just influenced by Bash. But let's go and take a look at it from programming language concepts and from this approach. Why is the eval function as defined by Lisp actually the right way to do it if we look at internal consistency within Lisp? And when we look at internal consistency, we've got to say, okay, eval, I know how car works, and I know how Qadr works, I know how atom works. Based on how I know all other functions work, eval is defined just the way it should be defined. In all programming languages that we know of, before a function is even called, before we even know what that function is, the system goes and evaluates the arguments and passes the evaluated arguments to the function. That's how it goes, unless you're doing lazy evaluation. And this is why Lisp is confusing, because it's got this lazy evaluation also. And it's confusing because we are doing the implementation, so we have a choice to evaluate or not. But in every language, arguments to a function evaluated before function call, before you even know what the function is. So you have to, in Lisp, you're basically saying evaluate the argument and then pass to the function whatever, the evaluate argument, it can do whatever it wants in addition. And we could have defined eval to be a no-op, but then why did we have an eval? So eval is a function that evaluates its evaluated argument. It makes perfect sense. Okay, from that point of view. Yet, a lot of us were confused about why eval list12 was giving an error because, yeah.
It's giving an error because, like I was saying, you shouldn't be doing that. Because, by definition of, well, if you're only doing it once, why are you calling eval on this anyway? You know that it's going to give you 1, 2. So, calling eval on it is pointless anyway because you know it's recurrent. So that's why this is consistent with that. You evaluate your argument.
No, so again, I'm going to say again that, I can always do eval twice and get what you want. So even with, even in a shell-like world, I would call eval twice. Okay? And so in the shell philosophy is you can enter something at the user level, or you can enter something at the program level, and they will have the same semantics. And right now, that is the philosophy I was using in my head when I gave the definition of eval. I said, we do eval within Lisp, and Lisp is also allowing you to call eval externally. And internally, when you call eval, you'll have to do eval twice to get what you want. Okay? So I can personally see both points of views, and that's why I think because Unix came later, they probably saw what Lisp had done, and they decided that they'd go with their semantics. And this sort of gets into language design issues. And the fact is that a lot of us almost everybody was confused last time, saying why eval list12 is giving, an error. So both points of views will allow the flexibility we want. Okay, it's a confusion factor that's there, and indeed in Lisp, you save on an extra eval when you want to really do an eval. Okay. Questions? Anybody got a bash open, by the way? No Mac user here? Okay. But we can do it offline. I was just curious. I'm glad you guys are listening to me. So not consistent with bash, consistent with other functions in Lisp and popular languages. And so, I think Lisp did get it right. And this is what brings us, and the reason why it's kind of confusing in Lisp is because Lisp is kind of schizophrenic, but in a very organized fashion, that for every function that we've seen, the arguments are evaluated before call, except for, go and look at these functions here, where are the exceptions? So, for all the functions, all arguments are evaluated before the function is called, except for code. That's the first answer. What's the second answer? All arguments are evaluated. Okay. So quote and con. Yeah, it's one argument is evaluated. It's kind of in between. Okay. Some but not all sub-expressions evaluated by cont. Okay. So so that's part of the confusion here. Okay. And okay, so but when we do lazy evaluation, we leave everything unevaluated, and but then we have to evaluate it correctly. It'll have to work the same way as this does for it to work. Okay. And the reason and what Andrew could have done was that he could have given you guys, so when he was designing his skeleton, he could have given your evaluators evaluated arguments, right? So that this whole issue wouldn't have arisen. Do I evaluate or do I not evaluate? Had he done that, cont and quote wouldn't have worked. Okay. So what I've seen implementation, a Lisp implementation of Lisp in Lisp, and what that does is before calling the specific functions, it does a special case for cont and quote. So whereas Andrew didn't want to do that, he wanted to make cont something that's extendable and not special. So that is the reason why we got into this trouble, because we don't want to make it non-extendable. So let's not do things that we shouldn't do. So let's not evaluate something that we don't want to do in few cases, and then the cases that do want to evaluate have to do the evaluate themselves. Okay. Okay. So that's basically all of A1, and now we want to get into A2's aspects. Okay. And we have been very constraining so far, or somewhat constraining in our input. So we know that an input X expression can be an arbitrary X expression as long that doesn't contain tuples, and we had two cases there. So that's a general case, but then we looked at two specific cases. So we said, look, that expression can be an atom. If it's an atom, it better not be a variable, better not be an identifier. We don't know how to handle identifiers, and otherwise it should be a function application. And that means it should have the first thing be a function, and that function better be a identifier, not a lambda. Okay, and it better be an identifier that identifies a basic function, not some user-defined function. Okay, so we have been very constraining in that way, and we want to relax that gradually. So